This video will examine nucleophilic substitution reactions. SN1 reactions are first-order reactions. This means that only one reactant is involved in forming the transition state, and therefore only one reactant determines the reaction rate. SN1 reactions involve the formation of an intermediate carbocation. This means that there is more than one discrete step during the reaction, unlike the SN2 reaction. The general mechanism proceeds as follows. Step 1. The carbon passes its shared electrons to the leaving group, forming a positive carbon ion in a negatively charged leaving group. Step 2. A nucleophile attacks the positively charged carbon ion, bonding with it. Let's examine the SN1 reaction of 2-bromo-3-methylbutane and water. First, the carbon passes its bonding electrons to bromine, forming a positive carbon ion and a negative bromine ion leaving group. Second, the 3,2 hydride shift occurs to increase carbon stability most often, though this only occurs where more stable carbon ions are possible. Third, whether or not a hydride shift occurs, a lone pair of electrons on water acts as a nucleophile to both of the products, attacking the positive carbon ion and forming a bond with it. Fourth, water attacks a proton who passes its bonding electrons to the hydroxyl group bound to the carbon forming an alcohol, a hydronium ion, and a negative bromine ion. This reaction results in a major product, 2-methyl-2-butanol, and a minor product, 3-methyl-2-butanol. In an SN1 reaction, the stability of the resulting carbon ion and the ability of the leaving group to depart determine the reaction rate. Therefore, compounds with more substituted carbons are the most likely to undergo SN1 reactions, with the fastest reaction rates. SN1 reactions proceed in a way that causes the groups attached to the carbon ion into a planar arrangement. Because of this, the nucleophile can attack from either side, and this can result in more than one possible compound when there are stereoisomers, or when attack from different sides results in mirror image non-similar molecules. Here's an image example of that situation. Finally, SN1 reactions often result in more than one product because of carbon ion stability and groups that shift accordingly. In class, we will discuss ways chemists will attempt to force an SN2 reaction to occur, and we will compare circumstances in detail that determine whether a nucleophilic substitution proceeds as an SN1 reaction with multiple products or as an SN2 reaction with one product.